In the first exercise, they ask you to find the nuclear radii of the following nuclide. So they say find the nuclear radii of the hydrogen with one proton and two, in this case, two nucleons, and the radii of the isolate element. They have 27, this should be cobalt, 27 protons and 60 nucleons, so there are like 33 electrons in that. So remember that if we want to find, we want to calculate, right, the radius, the outer radius, right? This radius of the nucleus would be r sub 0 times a to the power of 1/3, where r sub 0 is a constant and it's 1.2 times 10 to the negative 15 meters. So in this case, in my first case, I have that A is equals 2 because A is the number of nucleons. So for this first example, I can say that the radius would be r sub 0 times the cubic root of 2. So this should be 1.2 times 10 to the negative 15 meters times the cubic root of 2. So r would be, in this case, 1.5 times 10 to the negative 15 meters, which in Fermi is approximately 1.5 Fermi. It would be 1.5 Fermi or femtometer. Now we can do the same calculation for the other element. In this case, we have 60 nucleons, so A is equals to 60. So when we find the radius of this nucleus, right, we have that this is r sub 0, the cubic root of 60, and r sub 0, we know there is 1.2 times 10 to the negative 15 meters, cubic root of 60. So r would be, in this case, 4.67. So r would be, in this case, 4.67, sorry, 4.698, so approximately 4.7 times 10 to the negative 15 meters, which is equal to 4.7 femtometers or Fermi. So we have approximately a radius of 4.7 femtometers or Fermi. So really remember that in this case, if you want to find the radius, you know, the average radius, okay, of a nucleus, what you have to do is to use the constants r sub 0, and then here you have the cubic root of what? The cubic root of the number of nucleons. A is the number of nucleons. Remember that the nucleons are the sum of the protons plus the neutrons. The protons and the neutrons. So this is the first exercise that I had here for you. Let's solve one second exercise here. Let's say that an alpha particle with number of protons equals 2, a mass of 6.64 times 10 to the negative 27 kilograms approaches to within 1.0 times 10 to the negative 1.0 times 10 to the negative 14 meters, right, of a carbon nucleus that have Z equals 6. So you have 6 protons in a carbon nucleus. So they say, what is the maximum polar force of the alpha particle? What is the acceleration of the alpha particle at this time? And what is the potential energy of the alpha particle at this same time? Well, so what we have in this problem. So we basically have one alpha particle. There is this particle over here that have charge 2e positive that is moving with some velocity toward, a nucleus of carbon. I have 6 plus, 6e plus. So, and then, of course, this nucleus have positive charges, right? 6 positive charges. So what happened? The particle is moving, but at some point, this particle is going to turn around. This particle is going to turn around due to the action of the Coulomb force. We found that the distance, the maximum distance that this particle can approach to the nucleus is, or the minimum distance, sorry, that the particle can approach to the nucleus is 1.00 times 10 to the negative 14 meters. So we want to calculate what is the force of Coulomb. So remember that the force of Coulomb is equals K times Q1, Q2 over the square of the distance. Now what happens? We have that the charge of the alpha particle is 2e. So Q1 is the charge of the alpha particle, and it's equals to 2e. So it's 2 times the charge of the proton. So this charge will be approximately 3.20 times 10 to the negative 19 coulombs. You have then that the charge of the nucleus will be Q sub 2. This is the charge of the nucleus. The nucleus this nucleus have 6 protons, so it is 6 times the charge of the proton. When you multiply 6 times the charge of the proton, you will get that the charge of the nucleus is 9.6, approximately 9.6 times 10 to the negative 19 coulombs, right? So now we're ready to calculate the force, because we can say that this force is the Coulomb constant, 8.99 times 10 to the negative 9 newtons squared over Coulomb squared times the charge of the alpha particle. There is 3.20 times 10 to the negative 19 coulombs times the charge of the nucleus of carbon. There is 9.6 times 10 to the negative 19 coulombs, all divided by the distance, that this alpha particle approach, to the nucleus. So that is 1.00 times 10 to the negative 14 meters. And then we can calculate like that. This is a square, right? We can calculate like that the force of Coulomb. And the force of Coulomb, or electric force, that is the force of repulsion that makes the particle to turn around, is just equal to, in this case, 276.9 times 10 to the negative 1 newton. So this will be approximately 27.7 newtons. So the force between these two particles is 27.7 newtons. Now, we have to calculate also the acceleration of the alpha particle at this time, and then we know that the acceleration of the alpha particle would be equals to the force of Coulomb divided by the mass of the alpha particle. So remember that the force of Coulomb is the force that makes this alpha particle now to turn around. Okay, and then this acceleration is now the force of Coulomb that we found at 27.7 newtons divided by the mass of the alpha particle. There is 6.6 divided by the mass of the alpha particle. There is 6.64 was given this mass of the alpha particle times 10 to the negative 27 kilograms. And then we find the acceleration of this alpha particle is 4.17 times 10 to the 27 meters per second. Now, when we want to calculate now the potential energy of the alpha particle at this time, we have that the potential energy of the alpha particle will be K, the Coulomb constant, times Q sub 1, Q sub 2 over the distance between the particles, the particle nucleus. So this will be then now 8.99 times 10 to the 9 newtons meter squared per Coulomb square, times Q sub 1 is, well, we said 3.20 times 10 to the negative 19 coulombs approximately, times, I will just run to the small places, times 9.61, okay, 9.61 times 10 to the negative 19 coulombs. All this divided by the distance that we said that is 1.00 times 10 to the negative 14 meters. And we find that the potential energy in this case, right, the potential energy in this case will be equals to 1. We find that joules first, and in joules, it would be 2.76 times 10 to the negative 13 joules. And then later, when we convert these joules to electron volts, we get that this will be approximately 1.72 mega electron volts. So this is just in this case the potential energy of the particle. Right? So 1.72 mega electron volts. Let's do one more exercise. This exercise that I will solve next would be my last exercise today. Would be about the binding energy. And in this case, they give us an atom of magnesium with 12 protons and 24 neutrons. So we have to find the binding energy. So the nucleus of magnesium